And so I kind of wanna know a bit of the history of like just a tiny bit of the history of how did you start with LIGO and stuff like that.
Sure.
Yeah, who kind of, what was it that made that all happen?
Right. Well, I can briefly touch on that, but actually one of the things we're working on for the LIGO website right now is an
Yeah.
update of the history.
Okay, cool.
And there was some documentation prepared for the Nobel Prize ceremony,
Yeah.
which already gives, just in a really kind of publicly accessible way,
Okay,
a
cool.
timeline of.
Yeah, that's yeah,
So I'll send you that. It's
yeah.
like a
Just send me
one-page
that. Yeah,
PDF.
that's cool. That's
Yeah.
cool. Yeah, I just yeah.
But just to kind of take the highlights from that,
Yeah.
Essentially things kind of got going about 1960 or so.
Okay, cool.
And now Einstein's work on general relativity was longer ago than that, as I'm sure you know. It was back in the early decades of the 20th century.
Yeah.
But for a long time, everybody thought, yeah, general relativity, brilliant bit of theory, but we're never going to be able to detect these things. So there was a long gap where it sort of went into cold storage because the theorists loved it, but the experimentalists thought, waste of time, we'll never detect gravitational waves.
Yeah.
And the people that really helped to change that were Richard Feynman, very well-known physicist, and another guy called Joseph Weber. So Feynman helped to make the case that possibly you could detect these gravitational waves because, to go back to what we discussed at the beginning, effectively what they would do is cause space-time itself to vibrate.
Yeah.
And if you had a sensitive enough instrument, you could pick up those vibrations. So he helped to just start to shift opinion towards, well, maybe we should take a crack at this.
Yeah, yeah.
And then the first person to really take a crack at it was Joseph Weber. And what he was doing, remember I was talking about if you've got a bar of metal, you could put your ear against it and you would feel the vibrations.
Yeah.
So that's almost literally what he was trying to do.
Yeah.
He was trying to use a big bar of aluminium, or aluminum as they called it in the States.
Yeah.
And the idea being that as a gravitational wave passed by, it would make that bar vibrate.
Wow.
And then he would try and detect those vibrations. Now, if you remember, I talked about a millionth the width of a human hair.
Yeah.
So frankly, Weber was never going to be able to do this because he didn't have sensitive enough equipment.
Yeah, yeah, of course.
But because he gave it a go, it inspired a generation of scientists to think, well, maybe this is possible.
Yeah, yeah.
Let's think how we might do it. And the next big development was the mid-70s, where people realized that Weber's idea of using a metal bar was just like too optimistic. The metals wouldn't vibrate enough. But if you used a laser beam, then you would have a better chance, because what you would do is use essentially the arms of an interferometer. You maybe learned a little bit about that in A-level. Light shows interference patterns, and laser light would do that too. And the reason a laser is good for this is that we know the wavelength of laser light really incredibly precisely. And if you can send laser light back and forth along a beam tube many, many times, then even if there's only a tiny distance, a tiny difference in the path traveled by one beam, the beam that goes, let's say this way compared with the one that goes that way, then that will show up as a change in the interference pattern, because the two laser beams won't be lined up with each other anymore. So that's the basic design. You'll see all this in my TEDx talk. That's the basic design principle for the LIGO detector.
Awesome.
LIGO stands for Laser Interferometer Gravitational.
Nice. Yeah, nice.
And the reason they've got to be so big is that you're looking for such a tiny, tiny difference that you've got to send the laser light a long way before that difference shows up.
Yeah. This was the kind of this is where I was hoping to lead you into the next question. So yeah, you've kind of done it for me. So what are the challenges that you guys kind of face in terms of your, obviously you've got your small detection range. And yeah, what are you trying to do to, I guess, make that bigger?
Well, absolutely. See, the great challenges are engineering ones. You know, we understand general relativity well enough to do the job. I mean, we'd like to, you know, dot a few I's and cross a few T's on Einstein's theory, but for many years before the first detection, we kind of knew what we were looking for.
Yeah.
We knew what the signal should look like, but the problem was that if you follow this design principle of having a laser beam, you know, or two beams going in right angles, it's great in principle, but so many other things would affect those laser paths.
Yeah, yeah.
So if we go with this analogy of thinking of the gravitational waves more like a sound wave, I mean, they're not sound waves, but, you know, sound waves are vibrations of the air. So if we're thinking about vibrations of space-time, then actually thinking of them as sound waves isn't so crazy.
Yeah, of course.
It's quite a nice way to then see that all the disturbances that aren't gravitational waves, think of them like noise. They're like background noise.
Of course, yeah.
So the challenge we faced was picking out a known signal from incredibly loud background noise. So when we met in Toronto, the workshop I was doing with the kids there at the Science Centre was exactly that. It wasn't to do with physics as such. What we did was we gave them like a little random 5-word phrase, and they had to say that phrase over and over again. But meanwhile, one of the other groups of students was trying to drown them out. And they did that very well, you know, demonstrating the point that if they were, you know, banging their fists and stamping their feet and all of that, then the guys saying their secret phrase, you know, nobody else could hear a word of it.
Of course, yeah, yeah.
But once we quietened the guys doing all the background noise, once we quietened them down, then it was easy to hear the secret phrase.
So is it similar to kind of like CMS and stuff, where you take out what you already know and then you kind of look at the stuff that's left over?
Sort of. I mean, one of the reasons it's been such a joy working with Michael Hoch is that there's a lot of similarities in our approach, and therefore that little workshop I did with the kids in Toronto, we've done it lots of other places as well. Yeah. It's just as relevant to CMS, you're right, as it is to LIGO. The general principle is, how do you extract a known signal when there's a lot of background noise? And you know, it's a lot easier to do it if you know what you're looking for, but you've still got to try and reduce that background noise as best you can. So in LIGO's case, that was basically trying to stop the mirrors at the ends of the arms from shaking.
I see, okay.
Because, you know, if you're trying to measure a millionth the width of a human hair, the mirrors don't have to shake by very much, and you've completely swamped.
Yeah, wow. Okay.
So that was probably the biggest technological challenge, and that was what our group in Glasgow were leading the UK's contribution to. So, you know, you're funded by STFC for this project.
Yeah.
What STFC loved about all this wasn't just that the UK was part of it, but the UK had this kind of transformational role within it, because we developed ways to make the mirrors shake less, and that effectively was equivalent to kind of quietening down the background noise so that we could then hear the signals.